Welcome to the tutorial on encoders part 2.
Now let us solve a numerical and try to understand whatever concept we have just learned. Okay, so here is a numerical which says write a condensed truth table for a 4:2 line priority encoder with the valid output where the highest priority is given to the highest bit position or the input with the highest index, and obtain the minimal sum expression for the outputs. Clearly you need to read the line here properly. It says highest priority given to the highest bit position or input with highest index. This is very important because based on the question you have to change your priority. So what I am going to do is, first I will represent the truth table and I am going to consider the inputs because they have specified that it is a 4:2 line priority encoder. So let me consider x0, x1, x2 and x3 to be the inputs and y1 and y0 to be the outputs. So I am going to write the condensed truth table. Now since it is a 4:2 line priority encoder, I am going to number the cells in the first column. In the second column, I am going to specify my inputs x0, x1, x2 and x3. And in the third column, I am going to specify the outputs y1, y0. And in the fourth column, I am going to specify the validity indicator, whether it is valid or no. Okay. Now, in this particular case, x3 corresponds to the higher order bit. Okay. So this is having the highest priority as per the question. We can see that x3 is the one which is having the highest priority. So let me write that. Okay. So I have cell number, the inputs, 4 inputs, 2 outputs and a validity indicator. Now the first thing that I need to consider is whenever I have 4 inputs, I need to consider the case when all the inputs are 0. So when all the inputs are 0, we have clearly seen in the priority indicator that when all inputs are 0, outputs also will be 0, but that is not a valid case for us because we need to have any one of the bits to be logic 1, only then our output will be a valid case. So I am still considering this, that is because this is not a valid case. To indicate that it is not valid, I am considering this case wherein all inputs are 0 and outputs will be 0 and it is not valid. So that is why I have represented this as logic 0. Next combination. Let me consider the case when we have x0 to be equal to 1, remaining are all 0, 0, 0 and the output will be 0, 0. How I got this as 0, 0? Because see, when I represent this in terms of decimal number for a 2-bit output, what are the combinations that I can have? I can have the combination of 0, 0, 0, 1, 1, 0 and 1, 1. When I represent the decimal notation for 0, 0, it corresponds to 0. 0, 1, it corresponds to 1. 1, 0, it corresponds to 2. And 1, 1, it corresponds to 3. So, since x0 is equal to 1, clearly this corresponds to a decimal notation 0. So, I have y1 and y0 to be equal to 0, 0. Here, y1 is acting as the MSB bit and y0 is acting as the LSB bit. For the second case, I have x1, 0, 0. Why I have represented this as x1, 0, 0 is because I am specifying highest priority to the highest bit position or the input with highest index. So this is the input with highest index. So that means highest priority should be given to this one. So the lower order bit should not be given much priority. That is why when I come to the next case, it becomes x100. Now x100 corresponds to decimal notation 1, and in binary you represent it as 0, 1. Now, coming to the next one. You have XX10, XX10, this X2 corresponds to decimal notation 2, so that is why the output is 10, and here X3 corresponds to decimal notation 3, so that is why output is equal to 11. Now all these 4 cases are valid, that is because we have any one of the bits to be equal to 1, and since this is a priority encoder, we have given the priority to the highest order bit, so that is why the lower order bits are all XX, that is the don't care terms. That means they can be either 0 or they can be either 1. Cell number is 0 because all the inputs are 0. Here you can see this is 100. If you observe these combinations, 4 inputs means, 4 binary inputs means, you can have totally how many combinations? 16 combinations, that is ranging from 0 to 15. When I consider don't care terms, the don't care term can be either 0 or it can be either 1. When I represent 1000 in decimal, this corresponds to 8. Whereas when I represent this as 0100, this is equal to 4. Whereas if I consider this x to be equal to 1, then it becomes 1100, which gives me a value of decimal notation 12. In a similar manner, 0010 is 2, 0110 is 6, then you have 1010 is 10, 1110 is 14. So likewise, you have for the last cell, that is 0001 is corresponding to 1, 0011 corresponding to 3, 0101 corresponding to 5, 0111 corresponding to 7, and so on. Why this is logic 1, you might ask. In the question, it is not specified whether it is active low or active high. So I am considering the inputs to be active high. Okay. So when the inputs are active high, this is equal to 1, this is 1, this is 1, this is 1. Okay. Remaining on the upper end will all be equal to 0, whereas in the lower end all will be equal to x. If I would have given the highest priority to the lower or the least bit position, what would be the truth table? Highest priority given to the least significant bit, what happens is you will have 1 x, x, x. This would have been 0, 1, x, x. This would have been 0, 0, 1, x. This would have been 0, 0, 0, 1. Output will not change, but the representation will change here. And not only that, when this changes, accordingly your cell numbers will change, your decimal notations will change, and your simplified SOP or the minimal sum expression for the output will change. Now we have represented the cell numbers. So we have the outputs y1, y0, and we have validity. Right? So you can see y1 corresponds to minterm 1 for the cell number 2, 6, 10, 14, and you have 1, 3, 5, 7, 9, 11, 13 and 15. So if I want to represent y1, I need to consider both these cells, both these rows of cells to represent and simplify the expression. Whereas if I want to simplify and find out the expression for y0, I need to consider 4, 12 and I need to consider 1, 3, 5, 7, 9, 11, 13 and 15. Whereas if I want to simplify and obtain an expression for validity, I have to consider 8, 4, 12, 2, 6, 10, 14 and all the elements that are present in the last cell. So let me do that in the next case. So here I have x0, x1, x2, x3 as the inputs. I am considering x0, x1, x2 and x3, and like the way I had mentioned for the previous case, for representing y1, I have to consider both these cells. That is 2, 6, 10, 14, 1, 3, 5, 7, 9, 11, 13 and 15. So all these elements I am considering, I am mapping these minterms onto the Karnaugh map. Since there are 4 inputs, 4 variable Karnaugh map is required, and I am mapping the minterms, grouping them. I am grouping the minterms and finding out what is the simplified expression, and I obtain the expression as x3 plus x2. Now let me head backwards and see what should be the minterms that I need to consider for y0. 4, 12 and the last cells. Okay, so I have y0, 4, 12 and all the elements that are there in the last cell. I am going to map these minterms onto the Karnaugh map. So I have the 2 groups, the blue group and the yellow group. Now from the yellow group I obtain the expression x3, whereas from the blue group I obtain the expression as x1, and this will be equal to x2 bar. So that is why you have output y0 to be equal to x3 plus x1 into x2 bar. Now last one is the validity. For the validity you have to consider all the groups or all the elements except for 0. Okay, because what we said, 0, 0, 0 was not a valid case. So all the elements have to be considered except for the element 0. So when I do that, I am going to write all the minterms here. I am going to map the minterms. I am going to group the minterms, and I obtain the valid expression to be the sum of all the input variables. So you can see the input variables were x0, x1, x2, x3. So validity will be equal to all the elements that were there in the input variables x0, x1 plus x2 plus x3. So this is the way how you ensure that you get the correct result. Always your answer should give you a validity of the sum of the input variables that you have considered. As I mentioned, you can have a similar problem wherein the highest priority would have been given to the least significant bit. When you have highest priority given to the least significant bit, as we have discussed, we would be getting the reverse of this particular table with these bits being all zeros and these bits being all don't care terms. Then your cell numbers will change, your expressions for y1 and y0 will change, but your validity, will it change or will it remain the same? Because validity is equal to 0 only for the minterm corresponding to logic 0. In an encoder, we cannot have all elements to be equal to 0 because at least one of them has to be, any one line of the encoder input has to be active high or active low. So we cannot have where none of the inputs are active high or none of the inputs are active low. We cannot have such a case. So if such a case is there, that means it is not a valid encoder. So that is why when you are representing the validity part, the expression that you write will always be the same, whether you are giving the highest priority to the least significant bit or to the highest significant bit. So moving on, I have drawn a logic diagram here. This was not asked in the question basically, but sometimes if they ask you to draw the logic diagram also, because this question clearly was mentioned to obtain the minimal sum expression for the outputs, that is y1, y0 and validity. But in case if they ask you draw the logic diagram also, that is why I have drawn the logic diagram. So here what I am doing is I am just using the AND gate to represent x1 into x2 bar and a NOT gate because there is a NOT operation, then OR operation to represent y0, and directly I am using an OR operation to represent y1. So if this question is asked, you can also draw the logic diagram. Moving on to the second question. Design a priority encoder for a system with 3 inputs. Okay, with 3 inputs. The middle bit with highest priority encoding to 1 0, MSB with next priority encoding to 1 1, while the LSB with least priority encoding to 0 1. So, from the question, it says priority encoder with 3 inputs. Okay. So, I am having 3 inputs A, B, C. I am considering the MSB bit to be A. Okay. B is the middle bit. C is the LSB bit. In the question it is mentioned priority encoder with 3 inputs. So you have 3 inputs A, B and C. The middle bit with highest priority. So I am having this middle bit B, which I have numbered as 1 to show that it is having the highest priority. And this middle bit with highest priority will be encoded to 1 0. So if you observe, whenever there is a logic 1 corresponding to the variable B, my output, which is represented as YZ, will be encoded to 1 0. So you can see here, when you have B to be equal to 1, output is 1 0, B to be equal to 1, 1 0, B to be equal to 1, 1 0, B to be equal to 1, 1 0. Next, MSB with the next priority. So second, I have given the MSB bit priority. So A is having the second priority and it is encoding to 1 1. So this means whenever this is equal to 1, I am supposed to consider it to be a 1 1 case. Okay. Now, this is the second priority. We should remember that. Why I have already written the 1 0 and I am then going to write for the case of 1 1. That is because this is given the first priority, already output variables are written. So 1 0 is already specified. So next, when I am going for second priority, that is for the MSB variable A, this is 1. So that is why I am writing this as 1 1. This is 1, this is equal to 1 1. Now you may say this is also 1, this is also 1, so it's supposed to be 1 1. No. Because this was having the highest priority, 1 0 is already mapped. So though this is equal to 1 1, again I cannot change it to 1 1. So since this is highest priority, its outputs are already written. This is having the second priority. So only this one corresponds to YZ 1 1. This one will correspond to YZ 1 1. Next, last priority is given to the least significant bit. And in this particular case, LSB is the least significant bit. So here you can see you have a 1 here and this is given encoded to 0 1. So 1 is encoded to 0 1 here, and in this case we had this one to be having more priority, so it was already written, and here also this one was having a higher priority compared to this, so this one is already written. In this case also this one was having a higher priority than C, so it was already written. Then remains the case for all zeros wherein nothing is being specified. So output will be equal to all zeros. So YZ is equal to 0 0. So now let me represent this in terms of decimal notations. So I have the decimal notation. This is the inputs. So 0, 1, 2, 3, 4, 5, 6 and 7. I am representing the decimal notations for the input combinations that are specified. Now, to solve the to obtain the expression or to design the priority encoder, what I am going to do is, I am going to write the expression for output Y and expression for output Z. Now, if you look at the expression for output Y, you have the decimal notation 2, you have decimal notation 3, 4, 5, 6 and 7. So that is what is being specified here, summation M 2, 3, 4, 5, 6 and 7, and I am going to map these particular minterms, group these particular minterms and write the expression, simplified expression to be equal to A plus B. This is A, this will give me a group, this group will give me a variable B. Next, coming to variable Z. If you look at Z, the min terms will be corresponding to decimal notation 1, in this case decimal notation 4, in this case decimal notation 5. So 1, 4, 5. Clearly this is a 3 input variable. So that is why we have used a 3 variable Karnaugh map. I am going to map the variables 1, 4 and 5 and I get the expression as Z is equal to AB bar plus B bar C. Now, in this question, they have just mentioned design a priority encoder. They have not specified that whether you have to just stop at the obtaining the minimal sum expression. So when you say design the priority encoder, you may proceed by drawing the logic diagram also. So I have drawn the logic diagram with inputs A, B, C and I obtain the output Y, and this is the output Z obtained by considering A, B bar, I have used a NOT gate here, B bar plus B bar C, and that has been ORed to obtain expression Z. Next is decimal to BCD encoders. Now, priority encoders are plenty. You have 74148, 74LS148, 74HC148, and these are basically octal to binary priority encoders. But decimal to BCD encoders are 74147, which is a priority encoder, and this particular encoder is also called as the switch encoder. So let me explain with 74147 IC and its truth table. So basically a decimal to BCD encoder will produce the output code depending on which of its 9 input lines are active. Okay, depending on which of the 9 input lines are active. You can see you have inputs from A1 to A9. Depending on which of the input lines are active, you obtain the output. Okay, so specifically the 74147 is a decimal to BCD encoder with both the inputs and the outputs at active low. So that is why you can see that you have active low inputs, active low outputs. That is why everywhere you can see in this particular case validity will be equal to 0 for all 1 1 1 and outputs all 1 1 1, whereas validity will be equal to 1 for all remaining inputs. Okay, for all remaining inputs you have validity to be equal to 1, whereas when all the inputs are 1 and all the outputs are 1, validity will be equal to 0. So with an example, let me explain you. If you look at the input 7, okay, that is A7, when this particular input goes low, the outputs, that is O2, O1 and O0 are low. So when this input is low, these outputs are low. So such devices will be generally used in order to interface the numeric keypad to a microcontroller or a computer. Okay, and these don't care terms that you have seen here can either be 0 or 1. Because you have 9 inputs which are active low and the 4 inputs which are active low, the output that you obtain is an inverted BCD, if you observe here. And if you want to obtain a BCD output, what you need to do is you need to use a NOT gate here so that you get the correct BCD output. So let me explain that in the next slide. as to how as I mentioned, we are going to use this to interface the numeric keypad to a microcontroller or a computer. So usually we use this particular IC, that is 74147, for keypad interfacing. So you are going to have switches here, okay, which are connected to the inputs, and each of the switch will be pulled upwards with the help of a resistor that is connected to each of the inputs. So you have a 1 kilo ohm resistor from A9, you have another 1 kilo ohm resistor which is connected to this 5 volt, you have another 1 kilo ohm resistor connected to 5 volts. So from each of the input lines you have a 1 kilo ohm resistor, and all these switches are connected to the inputs. So you have totally 9 switches from 0 to 9. Depending upon whether the switch is open or closed, you will obtain the output. As I mentioned earlier, we have an active low input and active low output, and that was giving us an inverted BCD output. If you want to obtain a normal BCD, what we need to do is we have to use the NOT gate. So what we are going to do here is, depending upon whether the switch or the key is closed or open, we will decide our output. So when the inputs or when the keys that we have here, this key or the switch that we use is all open, all the inputs will be at logic 1, and when all the keys or the switches are closed, the corresponding output will be active low. So when the keys or the switches are open, you will have input 1 and output will be 1. When the keys are pressed, the output will be equal to logic 0. So this is basically a priority encoder, as we have seen, and this is an octal to BCD converter. Octal to BCD converter. So you have totally 9 inputs and you have outputs to be equal to 4. Looking at the next particular IC, that is 74148. Okay, this is an 8:3 priority encoder or octal to binary priority encoder. So in this particular case, you have totally 8 inputs and 3 outputs. The inputs are active low, outputs are active low, and you have an enable input and you have gray outputs which are active low. So 8 inputs, 3 outputs which generate the corresponding binary code. You have the priority which is assigned to each input, so that when 2 or more inputs are one at a time, the input with the highest priority is represented at the output, like we have seen in the priority encoder. And this particular IC, that is IC 74148, is one of the most popular ICs which is used in the medium scale integration circuits for 8:3 line priority encoder. And one of the main characteristics of this particular IC is that you are able to cascade this particular IC of n bits, and it is possible to use this particular IC for code conversion, for priority encoding of highest priority input line, decimal to BCD conversion, output enable active low of when all the inputs are high. So with this particular IC, let us solve one particular design scheme and see how we obtain. Okay. So you have various characteristics which are mentioned here. Now, coming to designing a scheme to transmit 8-line data over a 3-line. So here what we are going to do is, we will use one IC is 74148. This is the priority encoder IC which we saw just now. And next what we are going to do is, we are going to use a decoder, because the question says we need to design a scheme to transmit an 8-line data over a 3-line. So input is 8, output is 3. The way of transmission is 8-line data over a 3-line. So what we are going to do here is, we'll use an IC 74148, which is the priority encoder IC, and we are going to use an IC 74138, which is a 3:8 line decoder. Okay, this we have seen in the previous class when we studied the decoders. So here we used to use the G1 pin. So all these pins were meant for providing the enable. So G1 was always connected to the supply, and G2A and G2B was always grounded. Whereas in this particular case, we are giving G2A to GS. This will be at ground. And you have 8 inputs which are going to be transmitted over a 3-line. So this particular design scheme is just a specification or a design meant to tell you as to how we can transmit 8-line data over a 3-line. Okay.